So now we want to look at how we can transform variables. And let's look at an example, because this is something that's very useful. So here's my data again. I got rid of all the columns that I'm not going to use. I've still got my demand in monthly coffee sales in column A. Column B tells me my time period, each of the months, and I've got 2 years worth of data here. Then I've got my flag in column C for schools in session. Now I converted where it said no, I changed that to a 0. And I changed to where school's in session to a 1. So it's just 0, 1. 1 means it's in session, 0 means it's not. Because I think I'm going to develop another model, because I have the suspicion that not only is there a level, this beta knot, a trend, I think that some impact of the school being in session will increase my sales. And I think it's an absolute amount. So what am I going to do? I'm creating a new variable, this x3I, which is column C, and I'm defining this, and this is known as a dummy variable. And so it's saying that x3 sub I, where I is each of the observations, it's equal to 1 if the school is in session and equal to 0 otherwise. So that makes sense. That's what I did in column C. And so then the beta 3, the coefficient that I'm estimating here, how do I interpret that? Well, I would interpret that as an increase or decrease, depending whether it's positive or negative, in the demand in number of iced coffee sales per month when school's in session. So whatever that coefficient's going to be, if it's positive, then it's going to say, okay, when school's in session, that's how many more cups of iced coffee you're going to sell. When it's negative, it would assume just the opposite. There'd be a decrease in sales. So what we're doing here is trying to capture some effect. And this is one of the big benefits of using regression. We can isolate and try to capture the impact of different factors. So I do the same LINEST function, and again for my known x's, I'm going from B2 to C25, which is all of these. That's why I moved that variable for school in session over to column C. And then my other parameters 1 and 1. And if I do this correctly, I get this data table at the bottom. It should look very familiar by now. So here it is again. This is for the number 3 model, where I'm including both an intercept, a trend, and this is the estimate of the number of cups of coffee additional I can sell each month when school is in session. And so we're seeing, just looking at it really quickly, it's saying I should sell about 145 more cups of coffee whenever school's in session per month. So let's look at it a little more. What do? Overall fit of the model. The R squared went up. It's a 0.80, so that's pretty good. That's higher than the previous 2 models. Then I look at each of the individual coefficients and do the t-tests. And I'll let you look at the math, and you can pause the video if you need to, but you'll see and convince yourself that the intercept, the trend, are all still very valid at 0.0001. And then the school in session one, if we do the same t-stat, what do we get? Well, it's close, it's borderline, 0.105. So now you need to make a judgment call. Do I think this is worth keeping in or not? This is where some of the art and the science collide. Because if you're strict and you're saying, I only want things that are 0.01 significance or better in there, that's it, then you would throw that out. I personally would keep it in, because we can interpret it's telling me something pretty valuable. And so what this is saying, this model, the regression model, is that we're forecasting a monthly demand of about 3,156 iced coffees a month, right? That's up here, that's that beta knot, with a trend of about 52 additional cups per month. That's a trend. I just rounded it up. And whenever school's in session, I should see a bump of about 145 cups whenever school's in session. So this is my forecast going forward. So my forecast for January, year 3, which is the 25th period essentially, I just plug in those numbers, and school is not in session in January, so you come out to 4,444. February, I just add one more time period, right? 26 time periods instead of 25. And you see school is in session, so I'd expect to sell 4,640. So this is one transformation, dummy variables, very, very valuable to use, and they're very useful. But I can use other things. So the question you might have, though, for the dummy variables is they don't seem very linear. how can I use this dummy variable, which is binary, 0, 1? It doesn't seem like it's a linear function. And this is a fine point. The model needs to be linear in the parameters. And so if I look at the model, it's still linear in these functions, right? So I have the y is a function of beta naught plus beta 1 times the period plus beta 3 times this variable. The fact that this variable is 0 or 1 does not make this nonlinear. So we have to be linear in the parameters. And so that makes it a lot easier because we can do some other transformations. For example, this is the basic one we've been using, but let's suppose I wanted this, I think that there's some other trend here, and so I can have as my second variable the first one squared. So let's say this is the period, right? So time period 1, 2, whatever, and this is time period squared. What is this saying? This is saying it's still linear in the parameters, right? But it's saying that it's either going to look something like this, or if it's a negative term, it'll look something like this, where it dampens. Remember how we had dampened trends when we did exponential smoothing? Well, I could do the same thing here, and I would expect this beta 2 term to be negative, to be less than 0. So I could use this term, and you might say, well, how can I have that? It's a squared term. How can that be linear? It's because I'm linear in the parameters. Beta naught plus beta 1 times some variable plus beta 2 times some variable. The fact that that's the square of the previous variable doesn't matter. You can also do other kind of functions, transformations. For example, you can turn things using a logarithm. One thing is a multiplicative function. You can turn it into additive. And so you can have all these different things you can do. There are a lot of different transformations, and they're very valuable. So some other examples that you might want to do, and you can just test out different things. So looking at model 3, where I had the schools in session, maybe I think that it's not just whether the school's in session, but what the temperature is going to be. So I could create a new variable, call it x4, and it's simply that x3 variable, which was a 0, 1, times the temperature. So now what this means is this variable will be whatever the monthly temperature is when school's in session, and it'll be 0 otherwise. So this will only capture the temperature effect when school's in session. Again, you're still linear in those parameters. I can also do something like a variable x5. If I know that the coffee store across the street is running a sale, and I know that ahead of time, I can plug something in there. I can say x5 equals 1 if they run a sale at that time or they have additional competition. I can also do things like we talked before about squaring a term. Again, the critical thing is that you're linear in the parameters. So transformations are very powerful, very useful, but you have to be careful how you interpret the results, especially when you're dealing with natural logs. And then that goes beyond the scope of what we want to cover in this short lecture, but transformations, specifically dummy variables, very valuable.